There's a specific sensation that every gamer has experienced at least once. You're walking along a corridor, perhaps a bit too close to the wall, and suddenly the camera lurches. The textures stretch and warp. For a fraction of a second, you see through the geometry into the void beyond, that empty space where the game's illusion breaks down. Then you snap back into place, the physics engine correcting your position with a gentle push away from the wall. You laugh it off as a minor glitch, a small imperfection in an otherwise seamless virtual world. But what if you didn't snap back? What if instead of the engine correcting your position, it accepted your new coordinates as valid? What if the game decided that you are now on the other side of reality itself? This is the technical origin story of the Backrooms, though most people who encounter the creepypasta don't realise they're looking at a very specific type of software failure. The concept of noclipping through reality isn't just internet horror fiction. It's a reference to one of the most common and well-documented bugs in three-dimensional game engines. When someone says they've no-clipped out of reality, they're describing a collision detection failure so catastrophic that the player character's position becomes completely divorced from the intended playable space. The Backrooms mythos, which began with a single unsettling image posted to an image board in 2019, has grown into a sprawling collaborative fiction project. Hundreds of levels, entities, and narrative threads have been documented across wikis, YouTube videos, and creative works. But beneath all the horror and atmosphere lies something arguably more interesting. The Backrooms represent the most technically accurate depiction of what a catastrophic game engine failure might actually look like from the inside. Every element of the Backrooms, from the endless yellow hallways of level 0 to the reality-breaking impossibility of deeper levels, can be mapped directly onto specific technical failures in procedural generation, collision detection, and rendering systems. The humming fluorescent lights aren't just atmospheric, they're the visual representation of improperly culled light sources that should have been optimized away. The moist carpet isn't just unsettling, it's what happens when material properties get corrupted and default to semi-random values. The sense that rooms behind you aren't quite the same as when you left them. That's failed cache coherency. The engine unable to properly track state changes in unloaded sectors. This isn't to diminish the creative achievement of the Backrooms community. Instead, it's to highlight something remarkable. They've collectively reconstructed what the interior of a broken simulation might genuinely look like, using the shared cultural knowledge of game bugs and glitches as a foundation. Every person who has seen textures fail to load, who has watched an NPC vibrate violently against invisible geometry, who's accidentally walked through a wall that wasn't quite solid enough, brings that technical literacy to their understanding of the Backrooms. What we're going to explore over the next several hours isn't just the lore of the Backrooms. We're going to examine the actual technical systems that would need to fail for such a space to exist. We'll look at how collision detection works and how it breaks. We'll explore procedural generation algorithms and what happens when their seed values become corrupted. We'll dive into the mathematics of floating point precision and why coordinates far from the origin point inevitably become unstable. We'll examine how non-Euclidean spaces are actually rendered in game engines and how those techniques could theoretically scale to create truly impossible architecture. By the end, you'll understand the Backrooms not just as horror fiction, but as a surprisingly rigorous thought experiment about the nature of simulated reality and the specific ways such simulations fail. You'll recognize the technical fingerprints of source engine portal rendering, Unity's procedural generation systems, and Unreal's floating point coordinate spaces scattered throughout the lore. You'll see how the community has, perhaps without fully realizing it, created a comprehensive catalogue of every major category of game engine failure. The horror of the Backrooms isn't just that you're trapped in an endless maze, it's that you're trapped in a system that has broken down at such a fundamental level that the basic rules of space, causality, and physics no longer apply. You haven't entered a different dimension, you've fallen through the cracks in reality's own source code. And unlike a game where you can reload a save or restart the level, there's no console here. No way to type noclip again and return to the proper game space. You are, in the most literal technical sense, out of bounds, and the longer you stay there, the further you drift from the origin point, the more unstable everything becomes. The precision degrades, the geometry becomes less reliable, entities that shouldn't exist spawn in because the game is trying to populate an area that was never meant to be accessed. You're watching the simulation struggle to make sense of your presence in a space that exists only as optimization data, as bounding volumes and sector information that was never supposed to render. This is the technical horror of the Backrooms. Not monsters in the dark, though those exist too. Not even the isolation and endlessness, though those are certainly present. The real horror is being trapped inside a system that is actively failing, where each step forward takes you further into computational territory that becomes progressively less stable, less predictable, and less bound by the rules that keep virtual spaces coherent. So let's begin our deep dive into the machinery that would make such a space possible. Let's examine how reality's collision detection could fail, how its procedural generation could corrupt, and how its fundamental coordinate system could decay. Let's explore the Backrooms not as a supernatural phenomenon, but as the most comprehensive technical breakdown in simulation history. Welcome to the space between valid coordinates. Welcome to the out-of-bounds area that somehow generates content. Welcome to the place where the engine doesn't crash, it just keeps running, constructing impossible spaces from corrupted data and failing systems. Welcome to the technical specification of liminal horror. To understand how one noclips into the Backrooms, we first need to understand what a wall actually is in a three-dimensional virtual environment. This might seem obvious. After all, a wall is a barrier that stops your movement, right? But that understanding is actually backwards. In a game engine, nothing is inherently solid. Solidity is something that must be actively computed and enforced every single frame, for every single object that might potentially intersect with every other object. When you press forward on your keyboard and your character walks up to a wall and stops, what's actually happening is remarkably complex. The engine is calculating your character's intended position based on your velocity and the elapsed time since the last frame. Then it's checking whether that new position would cause your character's collision volume to intersect with any other collision volumes in the scene. If an intersection is detected, the engine has to decide what to do about it. Usually it prevents the movement, slides you along the wall surface, or applies some form of physics response. But all of this requires computation, checks, and systems working correctly. The wall itself is not doing anything. The wall is just geometry. A collection of vertices and polygons that exist in three-dimensional space. The wallness of the wall, its ability to block your movement, is entirely separate from its visual representation. In fact, in most modern games, the collision mesh, the shape used for physics calculations, is often completely different from the visual mesh you actually see rendered on screen. Let's talk about bounding volumes, because this is where noclipping becomes possible. The most common type of bounding volume is the AABB, the axis-aligned bounding box. This is exactly what it sounds like. A box, aligned to the world's coordinate axis, that encompasses an object. For a player character, this might be a box roughly 2 meters tall, half a meter wide, and half a meter deep. For a wall segment, it might be a thin box 4 meters wide, 3 meters tall, and 10 centimeters deep. AABBs are computationally cheap to test for intersection. You simply check whether the maximum and minimum coordinates of one box overlap with the maximum and minimum coordinates of another box along all 3 axes. If they overlap in X, and they overlap in Y, and they overlap in Z, then the boxes are intersecting and a collision has occurred. This can be done with just a handful of comparison operations, which is why it's the foundation of collision detection in virtually every real-time, 3-dimensional environment. But here's the critical weakness. AABBs only exist as data. They're not physical objects, they're mathematical abstractions. A typical AABB is just 6 floating point numbers: minimum X, maximum X, minimum Y, minimum Z, maximum Z, and the collision check. That's just code that runs every frame, comparing these numbers. If that code doesn't run, if it encounters an error, if the data gets corrupted, or if the positions being checked are somehow invalid, the collision simply doesn't happen. There are dozens of ways this system can fail. Let's catalogue some of the most relevant ones. First, there's the velocity problem. Collision detection typically works by checking whether objects overlap at their current positions. But what if an object is moving so fast that it teleports past a collision boundary between frames? Imagine your character's position is at coordinate x equals 0 in one frame, and the wall is at x equals 1. Your velocity would put you at x equals 2 in the next frame. The collision check sees you at x equals 0. No collision. Next frame you're at x equals 2. Also no collision. You've passed through the wall without ever technically intersecting it. Game engines solve this with continuous collision detection or swept volume tests, checking not just current positions but the path between them. But these are more expensive computationally, and they're often only enabled for certain object types or movement speeds. It's entirely possible for edge cases to slip through, especially in physics systems under heavy load or with unusual velocity values. Second, there's floating point precision. All those position coordinates we've been talking about, they're stored as floating point numbers, and floating point numbers have limited precision. Very small differences might get rounded away. 2 objects that should be just barely separated might have their positions computed as identical due to rounding errors. Or worse, an object might be computed as being on both sides of a boundary simultaneously, creating an undefined state that different parts of the code interpret differently. Third, there's the layer and mask system. Most game engines allow objects to be assigned to collision layers, with rules about which layers can collide with which other layers. Players might be on layer 1, walls on layer 2, triggers on layer 3. The player layer is set to collide with the wall layer but not the trigger layer. This is handled through bitwise operations on mask values. But what if an object's layer gets changed incorrectly? What if a bit gets flipped in memory? Suddenly a player might be on a layer that doesn't collide with walls at all. Fourth, and this is particularly relevant to the Backrooms concept, there's the question of what happens in spaces that aren't fully initialized. When a game level loads, collision data has to be passed, bounding volumes have to be constructed, spatial partitioning structures have to be built. What if you somehow end up in a part of the level that hasn't completed this initialization? The geometry might be there, the visuals might render, but the collision system might not yet know those walls exist. This is actually a common bug in open-world games with streaming systems. As you move through the world, distant areas unload from memory and new areas load in. Sometimes you can move faster than the loading system expects, arriving in a space where the visuals have streamed in but the collision hasn't. You fall through the floor or walk through walls, not because the collision detection failed, but because there was nothing there to detect yet. Fifth, there's the problem of one-sided collision. Many surfaces in games have collision on only one side for optimization. A wall that you can only ever approach from one direction doesn't need collision geometry on the backside. But what if you somehow get behind it? What if a bug in the movement system teleports you to the wrong side of a one-way collision surface? From that position, the surface is completely non-solid. You can pass through it freely because, from that perspective, it has no collision volume at all. Now let's bring all of this together into a scenario. Imagine you're playing a game, walking down a corridor. Your position is being updated every frame. The collision detection is checking your AABB against all relevant collision volumes. Everything is working correctly. But then, in a single frame, multiple small failures compound. Your velocity calculation introduces a tiny floating point error. The wall's position data experiences a brief corruption from a memory glitch. The collision layer mask has a bit flip from a cosmic ray hitting the RAM. The spatial partitioning tree that's supposed to quickly find nearby collision volumes returns an incomplete list because it was in the middle of updating. None of these individual failures would normally cause a problem. The systems have redundancy and tolerance built in, but in this one frame they all happen simultaneously. The collision check runs, but with subtly wrong data. It determines incorrectly that no collision is occurring. Your position is updated to the new coordinates, which place you 0.01 units inside the wall's volume. Next frame, the errors have cleared. The systems are running normally again, but now your position is already inside the wall's bounding volume. The collision resolution code activates, trying to push you out of the intersection, but which direction should it push you? The code examines the overlap, trying to find the shortest path to separate the volumes. Due to the specifics of your position and orientation, it calculates that the shortest path is further into the wall, deeper into invalid space. Your character model clips further into the geometry. More collision volumes are now intersecting. The resolution system is overwhelmed, trying to resolve multiple penetrations simultaneously. The math becomes unstable. Position corrections start fighting each other, and then, in the chaos of conflicting collision resolutions, your coordinates are updated to a value that places you completely outside the intended playable area. You've noclipped, not because you entered a cheat code, but because the collision detection and resolution system experienced a cascade failure from which it couldn't recover. And now you're in a space where different rules apply, because you're in a space that was never meant to be occupied. The engine doesn't crash, it doesn't throw an error, it just keeps running. It renders what it finds at your new coordinates. It tries to apply its normal rules to an abnormal situation. And what emerges from that process is something that looks very much like the Backrooms. This is why the concept of noclipping as an entry point to the Backrooms is so technically resonant. It's not just random weirdness, it's a specific failure mode that actually exists in real systems. Every game engine has out-of-bound spaces. Every collision detection system has edge cases where it fails. The Backrooms is what you might find if you fell through those cracks and the engine just kept simulating. The walls aren't solid because solidity must be computed and enforced, and if the systems that compute and enforce it fail, even briefly, even partially, you can slip through into the spaces between, into the areas that exist in the data but were never meant to be accessed, into regions where the geometry is present but the collision hasn't been properly initialized, where visual meshes exist but their corresponding physics volumes are malformed or absent. You're not in a different dimension, you're in the same simulation, just in a part of it that wasn't designed for occupancy. And that's when things get truly strange, because the engine doesn't know what to do with you there. It's going to try to keep simulating, keep rendering, keep generating content, but all of its assumptions about what should exist and how it should behave are now invalid, and that's when the procedural generation errors begin. Let's examine specific real-world examples of noclipping to understand how this phenomenon manifests in actual game engines, because the technical details matter for understanding how the backrooms would actually function. The Source engine, developed by Valve and used in games like Half-Life 2 and Portal, has particularly well-documented noclipping behavior because the engine includes a built-in noclip command for debugging purposes. When you enable noclip in a Source game, you're not actually disabling collision detection entirely, you're changing your movement mode to ignore collision responses. What's fascinating is what you see when you noclip through walls in Source engine games. The first thing you notice is that there's actually geometry on the other side of most walls, optimization volumes and simplified collision meshes that the player was never meant to see. These exist because the engine needs to know where the boundaries of the playable space are for lighting, calculations, AI pathfinding, and area portal culling. When you noclip, you enter this technical infrastructure space, the behind-the-scenes machinery that makes the game function. But if you keep going, moving further from the intended playable area, you start to see stranger things. Textures begin to stretch or repeat in unnatural ways, because the UV mapping was only correct within the expected view angles. Lighting becomes inconsistent or completely black, because light probes and light maps only cover the areas players can reach. And eventually, if you go far enough, you reach the edge of the map geometry entirely, emerging into an infinite void with just the skybox visible in all directions. This void state is important for understanding the backrooms. In most game engines, the skybox is always rendered at infinite distance, creating the illusion of a distant horizon or sky. But when you're outside the map geometry, you're in a space where only the skybox exists. There's no ground, no walls, nothing but the distant background. However, the engine is still tracking your position. Your coordinates are still updating as you move. You still have a position in three-dimensional space. It's just a position where nothing is meant to exist. Now imagine that instead of an empty void, this out-of-bound space had procedurally generated content. Not because it was intentionally designed that way, but because the engine's procedural generation system doesn't know it's not supposed to run there. The system that generates corridor segments or room layouts just sees coordinates being occupied and starts instantiating geometry. This is essentially what would need to happen for the backrooms to exist. You noclip out of bounds, and instead of finding nothing, you find an environment that's being generated by systems that don't realize they're creating content in invalid space. Unity Engine provides another instructive example. In Unity, collision is handled through collider components attached to game objects. A box collider, mesh collider, capsule collider, these define the shape used for physics calculations. But here's the key detail. Colliders can be disabled, removed, or fail to initialize. If you destroy or disable a game object's collider component while the visual mesh remains, the object becomes completely non-solid. You can walk right through it. This creates a specific type of noclip scenario where the world looks normal. All the geometry renders correctly, but nothing has collision. It's like being a ghost, passing through walls that appear completely solid. This is actually closer to how some interpretations of backrooms entry work. The world doesn't look different. Walls don't appear to have holes in them. But when you try to lean against one or walk past it normally, you just pass through as if it wasn't there. Unity's physics system also has a concept called layers and layer collision matrix, which defines which layers can physically interact with which other layers. A common bug occurs when an object gets assigned to the wrong layer during run time, perhaps due to a scripting error or a corruption of the layer field in memory. Suddenly, a player on layer 8 finds that walls on layer 2 no longer collide with them, even though walls on layer 3 still do. The world becomes selectively non-solid, with some barriers working and others failing, creating a confusing and unstable reality. Unreal Engine, particularly Unreal Engine 4 and 5, handles collision through a system of collision channels and responses. Each object broadcasts on certain channels and responds to others. A wall might block the pawn channel but ignore the camera channel, which is why you can put the camera through walls but your character can't walk through them. But channel data can become corrupted or incorrectly set. An object spawned with default settings might have collision responses that don't match what's expected. A wall that should block everything might be set to ignore pawns, creating an invisible passage through apparently solid geometry. One of the most detailed examples of real-world noclipping comes from speedrunning communities. Speedrunners have extensively catalogued collision failures in games because they are often exploitable for faster completion times. In the game The Elder Scrolls V, Skyrim, there's a technique called plate launching, where you pick up a plate object, hold it in front of you, and run into a wall while the plate is between you and the wall. The game tries to keep the plate from clipping into the wall by pushing it away, but since you're holding it, that force gets transferred to your character. With the right timing and positioning, this force can be so large that it launches your character through the wall at high velocity, bypassing the normal collision entirely. This is collision detection failing because of unusual force interactions, the physics solver creating velocities that exceed what the collision system was designed to handle. Your character's position updates so drastically in a single frame that continuous collision detection can't keep up, and you pass through barriers that should be impassable. Another speedrunning example comes from the game Portal, ironically enough, where portal-based movement can create situations where your velocity and position become desynced from what the collision system expects. If you place a portal on the floor and ceiling and fall through them repeatedly, you can build up enormous velocity. If you then redirect this velocity horizontally, and the collision detection can't handle the extreme speed, you can pass through walls that would normally be solid. The engine is trying to resolve portal transitions, velocity calculations, and collision detection all simultaneously and under extreme conditions. The systems can fail to coordinate correctly. There's also a category of noclipping that occurs due to physics object penetration resolution going wrong. In most physics engines, when two objects interpenetrate, the engine applies separation impulses to push them apart. But if objects are nested deeply inside each other, or if multiple objects are all intersecting simultaneously, the math for calculating the correct separation can become unstable. Sometimes this results in objects being launched at high speed. The infamous physics explosion where stacked objects suddenly scatter violently, but other times it results in objects being pushed into invalid positions that place them inside geometry they should never be able to reach. In the game Gary's Mod, which uses the source engine and gives players extensive control over physics objects, it's relatively easy to create scenarios where physics objects clip through walls. Spawn enough objects in a small space, let the physics engine struggle to resolve all the interpenetrations, and inevitably some objects will be pushed through walls into the void beyond. If the player is standing on or connected to such an object. They go along for the ride, no clipping through collision boundaries, not because of a collision detection failure, but because of a physics resolution failure. Now let's think about what happens after a no-clip event. In most games, one of several things occurs. First possibility: you fall into the void beneath the map, eventually falling far enough that the game decides you've died and respawns you at a checkpoint. Second possibility: you land on some out-of-bounds geometry that wasn't meant to be accessible, explore it briefly, and then either fall off into the void or use noclip again to return to the playable area. Third possibility: the game detects that you're out of bounds and forcibly teleports you back to a valid position. But what if none of those things happen? What if there is no void to fall into because the procedural generation system keeps creating floors beneath you? What if there's no out-of-bounds detection because the system wasn't designed to expect players in this space and thus has no triggers set up to detect them? What if there's no respawn because the game doesn't recognize that you've entered an invalid state? This is the scenario the Backrooms proposes. You've no-clipped, the collision failure has occurred, your coordinates are now in a region outside the intended playable space. But instead of the usual safeguards activating, the engine just keeps running. It keeps simulating, and because there are procedural systems active, systems that generate content based on position and seed values, those systems start creating an environment around you. The engine doesn't crash, because from its perspective, nothing is actually wrong. All the data structures are valid, all the systems are functioning within normal parameters. You're just at unusual coordinates, that's all. The rendering system sees your position and renders what exists there. The procedural generation system sees empty space at those coordinates and fills it with generated content. The physics system continues to simulate. The AI system continues to update entity behaviors. Now let's talk about infinite generation and what that actually means technically. When people describe the Backrooms as infinite, they're usually speaking metaphorically. But from a procedural generation standpoint, infinity is actually achievable, as long as the coordinate system can represent arbitrarily large numbers and the generation algorithm can derive unique seeds for arbitrary coordinates. The system can generate content without bound. However, there's a practical limit: floating point precision. Coordinates in games are stored as floating point numbers, and floating point numbers have limited precision. A standard 32-bit float has about 7 decimal digits of precision. This means that as coordinate values get larger, the spacing between representable values gets larger too. Near the origin point at coordinates 0, 0, 0, you can represent positions with millimeter precision. But at coordinates in the millions, the smallest representable step might be several centimeters. At billions, it might be meters. This precision decay affects procedural generation. When the algorithm tries to generate content at extreme coordinates, the position values it's working with are imprecise. 2 positions that should be slightly different might round to the same floating point value. Or positions might have strange gaps between them where no representable coordinate exists. The hash function receives less precise input, produces less precise seeds, and the generation output becomes less reliable. Minecraft provides a real-world example of this with the Far Lands, a phenomenon that occurred in older versions at extreme distances from the world origin. At coordinates beyond around 12 million blocks, the terrain generation started producing bizarre, glitchy structures, walls of terrain that shot up infinitely, impossible overhangs, areas where the normal noise functions that generate natural-looking terrain broke down into sharp, repetitive patterns. This happened because the coordinate values became so large, that floating point precision issues affected the noise function calculations, producing outputs that the terrain generation code was not designed to handle. The backrooms, if they followed this technical model, would experience similar degradation. Level 0, closest to the noclip entry point, might have relatively normal geometry. The procedural generation is working with coordinate values that, while out of bounds, aren't so extreme that precision becomes a major issue. The yellow hallways are strange and endless, but they're structurally coherent. Walls meet at right angles, ceilings are flat. The geometry makes sense even if the layout is disorienting. But as you travel further from the entry point, as your coordinates get more extreme, the precision decay begins to affect generation. Level 1, Level 2, deeper levels, the geometry becomes more unstable. Walls might not quite meet at corners, leaving small gaps or overlaps. Floor heights become inconsistent, creating subtle slopes where there should be level surfaces. Ceiling tiles don't align properly. These are the visual markers of a procedural system struggling with imprecise input data. Eventually, at extreme distances, the generation would break down entirely. Rooms might generate inside other rooms. Corridors might twist back on themselves in spatially impossible ways. Entities might spawn embedded in walls or floating in midair because their placement calculations are affected by the same precision issues. You'd reach a region analogous to the far lands, where the backroom's procedural generation produces output that is technically valid code execution but visually and spatially incoherent. There's another type of seed corruption worth discussing: temporal instability. Most games generate a world once at creation and then keep it stable. But what if the backrooms are continuously regenerating, constantly rerunning the generation algorithm? This could happen if the engine thinks you're exploring a new area every frame, if the caching system that's supposed to remember already generated chunks is failing, if memory pressure is constantly forcing the engine to discard and regenerate content. In this scenario, the seed might be stable, but the timing of when chunks generate could introduce variation. A chunk that generates on frame 1000 gets one set of random values from the generator's sequence. The same chunk generating on frame 2000, because the system forgot it already generated it once, gets different values because the generator is now at a different point in its sequence. The result is a world that flickers between states, where the environment subtly changes each time you look away and back. This could explain the entity behavior in Backrooms lore. Entities appear and disappear, seem to follow you, show up in places they shouldn't be. If entity spawning is part of the procedural generation system, and that system is constantly rerunning with slightly different timing or parameters, entities would appear to behave in ways that don't follow consistent rules. They're not intelligently hunting you, they're spawning in random but deterministically calculated positions that keep happening to be near the player because the player's coordinates are part of the spawn calculation input. Consider also what happens with level transitions. The Backrooms lore describes ways to move between levels, to noclip again, and fall through into deeper layers. From a technical perspective, this could be hitting a generation boundary, a point where the procedural system decides it can't continue generating content with the current parameters and needs to switch to a different generation rule set. This might happen when coordinates reach certain thresholds, when precision decay reaches a critical point, or when the algorithm detects that it's generated itself into an impossible state and needs to reset. The transition feels like falling through the floor because that's literally what's happening. The generation algorithm stops creating floor geometry at your position, either intentionally as part of a designed boundary or as a failure mode, and you fall until you reach the coordinate range where a different generation system takes over and starts creating floor again. You haven't moved to a different dimension, you've moved to a different region of the same coordinate space where different generation rules apply. Let's also examine what happens when multiple procedural systems interact. Real games often layer different procedural systems, one for terrain, one for structures, one for vegetation, one for entity spawning. These systems are designed to work together, with carefully managed dependencies and clear hierarchies. But in an out-of-bounds situation where you've no-clipped into the backrooms, those careful integrations might not exist. The terrain generation system creates the basic corridor layout. The structure system tries to add rooms and features. The decoration system places furniture and props. But because you're in space these systems weren't meant to populate, they might not coordinate properly. The terrain system creates a corridor. The structure system decides that same space should have a room, and you get a room embedded inside a corridor. Walls clip through walls. Furniture appears half buried in floors or hovering at ceiling height. Props spawn inside geometry. Every procedural layer is running independently, each following its own rules but with no coherent coordination between them. The result is an environment where multiple different spatial interpretations exist simultaneously, overlapping and conflicting. This is another form of non-Euclidean space, not geometry that curves or folds, but geometry that exists in multiple contradictory states at once, because different systems claim different things about what should exist at the same coordinates. From the player's perspective, this manifests as an environment that doesn't make sense. You see a door that leads to a room, but when you walk through it, you're in a corridor. Not because the room was hidden or the door was a trick, but because the rendering system is showing you the door that the structure generation system created, while the collision system is using the corridor layout that the terrain system created, and those two systems generated contradictory data for the same location. This is the deep horror of procedural generation in the backrooms context. It's not creating random chaos. The algorithms are deterministic, following clear rules, producing reproducible output. But the rules are being applied in a context they weren't designed for, with input values they weren't meant to handle, without the careful coordination and constraints that keep normal procedural generation coherent. The result is an environment that has the structure and logic of code execution, but the wrongness and impossibility of a fever dream. Every corner you turn was mathematically calculated. Every room you enter was deterministically generated from a seed value. Every entity you encounter was spawned according to specific probability distributions. But the calculations were done with corrupted input. The generation used parameters outside their intended ranges. The spawning probabilities were derived from positional data that introduced biases the developers never anticipated. The math is correct, but the context makes the output alien. And because it's procedural, because it generates endlessly based on your position, you can never escape it. Walking in any direction just triggers generation of more content. Backtracking doesn't help because caching failures mean the path behind you regenerates differently than it was before. You're trapped in an infinite space that's being constructed around you in real time by algorithms that are technically functioning correctly, but producing output that was never meant to exist. This is the procedural generation nightmare at the heart of the backrooms, an eternal maze that doesn't exist until you observe it, that changes when you're not looking, that extends infinitely in all directions because the generation algorithm has no concept of boundaries or endpoints. You're in a space where mathematics has replaced geography, where seed values and hash functions determine reality, and where every step forward is a request for the universe to calculate what comes next, and it always has an answer. The generation never fails completely, never returns null, never gives up. It just keeps producing output, keeps creating corridors and rooms and spaces, each one mathematically valid and individually coherent, but collectively forming a labyrinth that human minds were never meant to comprehend. This is what happens when you fall through the cracks of reality into the procedural generation layer beneath, the computational substrate that creates worlds on demand without understanding or intention, only execution of algorithm. When people describe the backrooms as non-Euclidean, they're usually referring to the sense that space doesn't work the way it should. Corridors that seem longer when you walk down them than they appeared from the entrance. Rooms that are bigger on the inside than the outside. Spaces that loop back on themselves in ways that shouldn't be possible. This isn't just artistic license or metaphorical description. It's achievable through specific rendering techniques that game engines actually use. True non-Euclidean geometry in the mathematical sense involves curved space where parallel lines can intersect or diverge, where the angles of a triangle don't sum to 180 degrees, where the shortest path between 2 points isn't a straight line. That's not what we're talking about here. What we're discussing is impossible spaces within Euclidean geometry, spaces that violate the player's expectations of how three-dimensional space should behave. And game engines have been creating such spaces for decades. The foundational technique is portal rendering, and the source engine is the canonical example. In the game Portal, you can create two connected portals, and when you look through one, you see the view from the other. This is accomplished through clever rendering tricks. When the engine is drawing the scene from your perspective, it detects that you're looking at a portal. It then renders a second view from the position of the connected portal, oriented to match your viewing angle, and displays that rendered view on the surface of the portal you're looking at. This allows for impossible spaces. You can have a small room with a portal on the wall. Through that portal, you see a massive warehouse. When you walk through the portal, you're genuinely in the warehouse, with all its space and scale. But from outside, the warehouse doesn't exist in the world space. It's in a completely disconnected area of the map, only accessible through the portal connection. The physical layout of the game world doesn't need to make geometric sense, because space is partitioned into discrete areas, connected by portals rather than by continuous adjacency. Now imagine this technique applied not just to intentional portal devices, but to every doorway and corridor transition. Each door is secretly a portal leading to a space that isn't physically adjacent to the room you're in. You walk through what appears to be a normal doorway, but you're actually teleporting to a completely different region of the map. The corridor on the other side could be oriented in any direction, could be at any location because the connection is virtual rather than spatial. This is how truly impossible Backrooms geometry could function. Level 0 appears to be an endless grid of corridors, but it's not actually a continuous space. Each corridor segment is a discrete area. When you walk from one segment to another, you're portal transitioning. The generation algorithm can place the next segment anywhere, in any orientation, because continuity is maintained through portal rendering rather than through physical adjacency. From the player's perspective, it looks seamless. You see the next corridor through the door where you walk through, you're now in that corridor. But the actual coordinate space has jumped. You went from position x equals 1000 to position x equals 5 million in a single step. But the transition was masked by the portal rendering. This allows the environment to be infinite not by extending infinitely in coordinate space, which would eventually hit floating point precision limits, but by being a network of finite spaces connected through portal transitions. It also enables the non-Euclidean properties. a corridor that appears to be 50 meters long when you look down it, but when you walk it, you pass through 5 portal transitions, and you've actually traversed 200 meters of coordinate space. The visual length doesn't match the traveled distance because the space is being folded, with portals creating shortcuts or extensions that aren't visible to the player, or consider a loop that shouldn't exist. You walk forward through 4 doorways, turning right at each one. After the 4th turn, you should be back where you started, facing the same direction you began. But you're not. You're in a different room entirely. How? Each of those doorways was a portal. The rooms aren't actually arranged in a square, they're scattered across the map in arbitrary positions. The portal connections create an apparent square loop in navigation space, but the actual spatial arrangement is completely different. This technique can create spaces that are larger inside than outside, the classic TARDIS effect. A small room, 5 meters by 5 meters. You walk through a door. The room you enter is 50 meters by 50 meters. But when you turn around and look back through the door, you see the small room you came from, appearing to be the same size it was before. How is the large room fitting inside the small room? It's not. The large room is elsewhere in the map. The doorway is a 2-way portal. Looking through it from one side shows the small room. Looking through from the other shows the large room, but they're both rendering views from distant positions. The source engine implementation has some limitations because portals are performance intensive. Each active portal requires rendering the entire scene from an additional viewpoint. If you can see 5 portals simultaneously, the engine might need to render 6 complete views of the world. Your normal view plus 1 for each portal. This is why Portal the game typically limits you to 2 active portals and carefully designs levels so you can't see one portal through another portal, avoiding recursive rendering requirements. But the backrooms wouldn't need to follow these constraints. If the environment is procedurally generated and the generation algorithm can control what you see, it can ensure you never have sightlines that would require rendering many portals simultaneously. Corridors are long and straight, limiting view distance. Rooms are separated by doorways that act as portals, but don't require rendering the destination until you're close. The impossible geometry is hidden by careful control of visibility and sightlines. Another technique for creating non-Euclidean spaces is coordinate system manipulation. The game engine tracks positions using a global coordinate system, but what the player experiences can be manipulated. You could have a corridor that's only 50 meters long in actual coordinates, but as the player walks down it, their movement speed is secretly being reduced while the rendering is adjusted to make it appear they're moving at normal speed. They think they're walking at 5 meters per second, but they're actually moving at 1 meter per second. The 50-meter corridor takes 50 seconds to traverse instead of 10, making it feel much longer than it appears. This can be done dynamically based on the player's position. As they approach the end of the corridor, their movement speed increases back to normal. The transition is gradual enough that they don't notice the change in speed, but they register that the corridor took longer to walk than it should have. The space has been perceptually stretched without actually being geometrically larger. Or consider the inverse, compression of space. A corridor that appears to be 200 meters long in the distance. As you walk toward it, objects in the distance approach faster than they should based on their apparent position. You're moving at normal speed in coordinate space, but the rendering is manipulating perspective and scale to make distant objects closer than they appear. You traverse the apparently 200-meter corridor in the time it should take to walk 100 meters. Combining these techniques with the procedural generation we discussed earlier creates an environment where space itself becomes unreliable. A room generates with specific dimensions, but the portals in its doorways lead to rooms that don't match those dimensions. The corridor connecting two rooms is rendered as shorter than the coordinate distance between the rooms. The player's movement through the space is subject to speed manipulation that makes distances inconsistent. Navigation becomes impossible because there's no coherent spatial map. You can't sketch out the layout because the layout isn't consistent. The path from room A to room B isn't the same distance each time you walk it. Rooms connect in ways that change based on which direction you approach from. The environment has topology, the abstract connectivity of which spaces lead to which other spaces, but it doesn't have stable geometry. This is mathematically similar to non-Euclidean manifolds in physics, where space has consistent local properties but globally is curved or connected in ways that defy Euclidean intuition. In the backrooms, each individual corridor or room is Euclidean, walls are perpendicular, floors are flat, normal geometry applies. But the global structure, how all these spaces connect to each other, doesn't obey Euclidean rules because portal connections and coordinate manipulations have broken the relationship between local and global geometry. There's also a technique used in some horror games called view-dependent rendering, where the environment literally changes based on what you're looking at. When you look at a corridor, it renders with one layout. When you look away and then look back, the rendering calculates a different layout. From a technical standpoint, this is similar to how reflection probes work, pre-rendering views of the environment from specific positions to use for reflective surfaces. Applied to the backrooms, this could mean the environment only fully exists when observed. Turn your back on a hallway, and instead of remaining in memory in its current state, it unloads. Turn around again, and it regenerates. Potentially differently than before if seed values or generation parameters have changed. The flickering instability of the space isn't supernatural, it's literal. The rendering system is only maintaining detail for what you can currently see and regenerating everything else on demand. This would explain why entities seem to move in ways that don't make sense, why rooms aren't where they should be when you backtrack, why the environment feels like it's responding to your observation. It's not intelligent, it's not aware. It's just a rendering optimization taken to an extreme where only the currently visible portion of the world is actually instantiated, and everything else is probability space waiting to collapse into concrete geometry when you turn to look at it. Modern game engines have started experimenting with even more aggressive forms of this with techniques like Nanite in Unreal Engine 5, which only renders the exact triangles that will be visible from your current viewpoint, dynamically loading and unloading geometry at a very fine scale. If you took this concept to its logical extreme, the entire environment would be in a state of constant flux, streaming in and out of existence based on what you can see. For the backrooms, this could mean that there's no persistent world at all. The environment only exists as an interface layer between you and the procedural generation algorithm. You request a view by looking in a direction. The algorithm calculates what should be visible from that viewpoint given your current position and the world seed. The rendering system displays that calculated result. When you move or turn, the calculation runs again, producing the next view. The corridors don't exist when you're not looking at them. They're not even stored in memory. They're potential states that become actual only through observation. This is the non-Euclidean horror of the backrooms taken to its ultimate technical conclusion. Space doesn't exist as a persistent geometric structure. It exists as a procedural function that takes your position and view direction as input and returns a rendered scene as output. Move to a new position, and the function runs again. Look in a different direction, and the function runs again. Each time it's calculating what should exist, not retrieving what does exist. You're not moving through space, you're querying a space-generating function. And because it's a function, it can return impossible results. It can tell you that the corridor to your left is 50 meters long, while simultaneously telling you it's 200 meters long when you actually walk it. Because those are two different function calls with different contexts. It can show you a room through a doorway, then when you pass through that doorway, execute a completely different calculation that produces a different room. The geometry is non-Euclidean not because space is curved, but because space doesn't exist as a unified structure. It exists as a collection of localized, context-dependent calculations that produce outputs which don't need to be globally consistent with each other. Each view, each moment, each position is its own isolated calculation. And the horror is that you can't escape it because you can't get outside the system. You're always inside a calculated view. There is no underlying reality to find, no true layout to discover. There's only the function, executing endlessly, producing views and spaces that obey their local rules but don't cohere into any possible global configuration. This is how non-Euclidean geometry would actually work in a game engine context for the Backrooms. Not through mathematical tricks with curved space, but through fragmentation of space into disconnected pieces linked by portals, coordinate manipulations, and view-dependent generation. The result is an environment that feels wrong at a deep level because our spatial intuition expects continuity and consistency, but every technical detail of how the space is constructed violates those expectations. Now we need to address what happens at the deepest technical level, the mathematics that underlies all position and movement in three-dimensional space. Everything we've discussed so far, collision detection, procedural generation, portal rendering, depends on coordinate values to specify where things are. And those coordinate values are stored as floating point numbers. Understanding how floating point numbers work and how they fail is essential to understanding the technical reality of the deeper Backrooms levels. A floating point number is a way of representing real numbers in binary with finite precision. A standard 32-bit float, which many older game engines use, consists of a sign bit, 8 exponent bits, and 23 mantissa bits. This structure allows representing a huge range of values, from around 10 to the negative 38th power up to 10 to the 38th power. But here's the critical limitation. You only get about 7 decimal digits of precision. What this means in practice is that as numbers get larger, the gaps between representable values get larger too. Near 0, you can represent numbers like 0.00000001 with reasonable accuracy. But at 1 million, the smallest difference you can represent is around 0.1. At 1 billion, the smallest step is around 100. You literally cannot store a number like 1 billion.5 in a 32-bit float. It rounds to 1 billion or 1 billion and 100. But the intermediate values simply don't exist in the representation. For a game engine, this creates a practical limit on world size. If your game world extends millions of units from the origin point, positions far from the origin suffer from precision issues. An object at position x equals 10 million cannot be positioned with fine precision. Its position will snap to the nearest representable value, which might be several units away from where you actually wanted it. If you try to move it by a small amount, less than the precision threshold, nothing happens. The movement gets rounded away to 0. This is the origin of the far lands in Minecraft and similar phenomena in other games with large worlds. At extreme distances from the world spawn point, the coordinate values become so large that floating point precision breaks down. An entity that should be standing on a surface hovers slightly above it, or sinks slightly into it because the vertical positions can't be represented with enough precision to make them exactly match. Blocks that should align perfectly have small gaps or overlaps. The visual jitter as entities move is because each frame, the rendering system is trying to place them at positions that round to different representable values. For the backrooms, we can use this phenomenon to explain the progressive instability of deeper levels. Level 0, being closest to the entry point, would have coordinates that aren't too far from the origin. Perhaps you noclip at position x equals 5000, y equals 1000, z equals 2000. At these coordinates, floating point precision is still quite good. Millimeter level precision is achievable. The geometry generates cleanly, positions are stable, movement is smooth. The space feels wrong because of the endless maze and strange aesthetic, but technically it's solid. Level 1 might be further from the origin, perhaps at coordinates in the hundreds of thousands. Precision is degrading. Now you can only represent positions to within a centimeter or so. Small objects might not place exactly where they should. Textures might not align perfectly at the pixel level. You start to see visual artifacts, slight gaps between wall panels that should be flush, floor tiles that don't quite line up, objects that hover a tiny bit above surfaces. These are subtle. You might not consciously notice them, but they contribute to an uncanny feeling that something is slightly off. Level 2, further still. Coordinates in the millions. Precision is down to maybe 10 centimeters. Movement becomes noticeably jittery because each frame, your position rounds to different values that are 10 centimeters apart. Objects vibrate slightly because their positions oscillate between the limited set of representable coordinates. Walls that should be straight have a subtle waviness. To them, because the vertex positions can't be represented precisely enough to maintain perfect linearity. The geometry is degrading into perceptible wrongness. Deeper levels, coordinates in the tens or hundreds of millions. Precision is now measured in meters. Positions snap to a coarse grid. Entities can't stand smoothly on surfaces because there aren't enough representable values between surface height and character height to allow stable positioning. Collision detection starts failing because objects are constantly rounding into and out of contact with each other. A wall might be non-solid from one side because your approach vector rounds your position to values that happen to be on the other side of the wall's collision volume. At extreme distances, coordinates in the billions or beyond, this space becomes fundamentally unstable. Precision is down to hundreds of meters or worse. The concept of a position being precisely defined breaks down. Procedural generation tries to create detailed geometry, but the coordinates it calculates can't be represented accurately, so vertices round to a tiny number of discrete positions. Walls collapse into flickering planes because there aren't enough representable coordinates to define their shape. Entities can't navigate because pathfinding requires precision that doesn't exist at this scale. This is the technical explanation for why the Backrooms law describes deeper levels as increasingly incomprehensible and unstable. It's not metaphorical deterioration of reality. It's literal mathematical decay of coordinate precision. The further from the origin you get, the less precisely anything can be positioned, and without precise positioning, all the systems that create coherent three-dimensional environments break down. There's also a phenomenon called catastrophic cancellation in floating point arithmetic that's relevant here. When you subtract two very similar large numbers, you lose precision dramatically. Imagine you have two coordinates that are both approximately 10 million, and you need to calculate the difference between them to determine the distance between two objects. In exact mathematics, 10,000,000.1 minus 10,000,000.05 equals 0.05. But in floating point, both original numbers might round to 10 million, and the subtraction yields 0. Or they might round to slightly different values, and you get 0.1 instead of 0.05. This affects any calculation that involves differences or deltas. Distance calculations become unreliable. Collision detection, which depends on calculating penetration depths, fails in unpredictable ways. Physics simulations, which integrate forces and accelerations by computing small changes in velocity and position, accumulate errors rapidly. An entity that's supposed to gently settle onto a surface might instead vibrate wildly or launch off at high speed because the physics solver is working with corrupted delta values. Game engines have developed workarounds for these issues. One common technique is origin shifting. When the player gets too far from the origin, everything in the world gets shifted by a large offset to bring the player back near 000 without actually moving them relative to the world. From the player's perspective, nothing changes, but in coordinate space, a massive shift has occurred to preserve precision. But for the backrooms, these workarounds wouldn't exist. You've no-clipped into unmanaged space. The origin shifting system doesn't know you're there and doesn't reposition you. Or perhaps it tries to but fails because your position is flagged as invalid in some way that prevents the shifting code from running correctly. So you just keep accumulating distance from the origin as you explore, and the precision decay continues unchecked. Another aspect of floating point error is that it's not uniform or predictable. Certain values are represented exactly, others are approximations. The errors compound in ways that depend on the specific sequence of operations performed. Two players who take slightly different paths through the backrooms might experience different floating point errors, accumulating in different ways, leading to divergent experiences of the same nominal space. This could explain why backrooms explorers report inconsistent experiences. It's not that the levels are randomly different for different people, it's that the floating point errors affecting each player's simulation diverge based on the exact history of their movements and the specific calculations performed. Your reality and another explorer's reality are running on the same underlying algorithms with the same seed values, but accumulating different rounding errors produces different perceived geometry and behavior. There's also the question of what happens with 64-bit doubles instead of 32-bit floats. Modern game engines often use doubles for precision-critical calculations. A 64-bit double has about 15 decimal digits of precision instead of 7, which pushes the Farlands phenomenon out to much greater distances. At coordinates in the trillions, you'd still have millimeter precision, but even doubles have limits, and more importantly, not all calculations use doubles even in engines that support them. Graphics card operations often still use 32-bit floats for performance reasons. You could have a situation where gameplay logic is calculating positions with 64-bit precision, but when those positions get sent to the rendering system, they're converted to 32-bit, introducing precision loss in the visual representation, even though the underlying simulation is still precise. This could manifest as a disconnect between where things are and where they appear to be. An entity's actual position, as far as collision and gameplay logic are concerned, might be precise, but its rendered position, what you see on screen, is a rounded approximation. You try to interact with an entity, but you miss because it's not quite where it appears to be, or you collide with a wall that appears to be several centimeters away because the wall's visual position is rounded differently than its collision position. The deeper Backrooms levels could exhibit this as a persistent misalignment between visual and physical reality. What you see is not quite what exists. The space appears to have a certain geometry, but when you move through it, or interact with it, you discover that the physical reality doesn't match the visual, not because of intentional illusion or trickery, but because the visual rendering and the physical simulation are working at different precision levels and rounding differently. All of this floating point instability feeds into procedural generation in devastating ways. Remember that procedural generation depends on coordinates to derive seed values for different chunks or regions. If those coordinates aren't stable, if they're rounding and fluctuating due to precision issues, the seeds derived from them become unstable too. The same position might produce different seeds on different frames or different playthroughs because the floating point rounding goes different ways based on subtle differences in calculation order or intermediate values. This means the environment itself becomes non-deterministic at extreme coordinates. The procedural generation algorithm is deterministic. Same input always produces same output, but the input is now unstable due to floating point errors. So the same nominal position produces different generation output at different times. The space flickers between possible states, not because of supernatural reality shifting, but because the mathematical substrate is too degraded to maintain consistency. This is the final layer of technical horror in the Backrooms. This space isn't just endlessly generated, non-Euclidean in its connections and perceptually unstable. At a fundamental mathematical level, the precision of reality itself decays as you go deeper. The numbers that define where things are and how they behave lose their accuracy. And as those numbers degrade, every system built on top of them degrades in turn. Procedural generation becomes inconsistent, collision detection becomes unreliable, rendering becomes misaligned with physics, entity behavior becomes erratic. You're descending through layers of mathematical abstraction, and at each layer you're finding that the abstractions are breaking down. The high-level gameplay experiences the deep-level numerical instabilities as reality itself failing. And there's no fix, no way to restore precision because you're too far from the origin, and there's no path back. Every step you take in any direction just increases your distance from 000, further degrading the mathematics that underlies your existence in this space. This is what the deeper levels of the Backrooms would actually be like from a technical perspective. A progressive descent into mathematical chaos, as the finite precision of floating point numbers proves insufficient to maintain coherent simulation at extreme coordinate values. The horror isn't supernatural, it's computational. You're watching the simulation struggle to represent your existence, and failing one degraded calculation at a time. Now that we understand the underlying technical systems, let's examine how they would manifest in specific Backrooms levels. Each level in the established law has distinct characteristics, and we can map those characteristics to specific types of technical failures and generation parameters. Level 0, the iconic yellow hallways with moist carpet and fluorescent lights, represents the most stable form of corrupted space. The procedural generation here is working relatively well. It's just operating in an area it wasn't meant to populate. The coordinates aren't so extreme that floating point precision is a major issue. The geometry is simple. Corridors at right angles, flat ceilings, uniform wall spacing. This simplicity suggests a basic procedural algorithm, perhaps something like a grid-based maze generator running with minimal parameters. The yellow color and specific texture choices could be explained as default values. When a material system doesn't receive proper texture assignments, it often falls back to defaults. Yellow might be the default albedo color in whatever generation system is creating these spaces. The carpet texture, described as moist or damp looking, could be a material property corruption, where the normal map or specular values are wrong, creating an appearance of wetness that shouldn't exist. The fluorescent lights are particularly interesting from a technical standpoint. They're described as humming, flickering occasionally, and creating that distinctive office building ambience. But from a rendering perspective, those lights should have been optimized away. In a properly designed level, lighting would be baked into light maps, static pre-calculated illumination that's sufficient to render. The fact that the lights are individual entities that hum and flicker suggests they're dynamic lights, real-time light sources that recalculate every frame. Why would the procedural generation create dynamic lights when static would be more efficient? Possibly because the generation code is creating these spaces on the fly and doesn't have time to bake lighting. Or the lighting baking systems don't run on procedurally generated content. Or the light baking completed but the data got corrupted, forcing fallback to dynamic lighting. Either way, those humming fluorescents are a sign of a rendering system under strain, using expensive real-time calculations because proper optimization isn't available. The endless nature of level 0 is pure procedural generation. As you walk, the system generates new corridor segments ahead of you and potentially unloads segments far behind you to manage memory. But there's a cache coherency issue we'll discuss in detail later. The system isn't properly tracking what it's generated, so when you backtrack, segments regenerate differently. The maze isn't consistent because the generation is stateless, recalculating each chunk based solely on position and seed without memory of what it created before. Level 1, often described as industrial or warehouse-like with concrete and exposed pipes, represents an increase in generation complexity. The procedural system is now creating more varied geometry, storage racks, machinery, multi-height spaces with catwalks. This increased complexity means more things that can go wrong. The industrial aesthetic could be the algorithm selecting from a different texture set, perhaps a set meant for basement or utility areas in a normal game world. The description of level 1 often includes large open areas alternating with tight corridors. This could be a procedural generator that creates rooms of variable size, with a probability distribution that occasionally produces very large spaces. But the transition between these spaces might not be handled correctly. In a properly designed level, large open areas would use different rendering techniques than tight corridors. Occlusion, culling wouldn't work the same way. Lighting would need different approaches. Audio reverb would change. If these transitions aren't managed because the procedural system doesn't know how, you get jarring shifts in how the environment feels and performs. The presence of entities in level 1, often described as smilers or hounds, could be the result of an entity spawning system that's part of the procedural generation. The system is designed to populate areas with AI characters, but it's using corrupted spawn tables or probability distributions. Instead of spawning normal NPCs, it's spawning entity types that are malformed or from unused content, creating the unsettling creatures the lore describes. Level 2, maintenance tunnels and service corridors, pushes the technical instability further. The aesthetic shifts to darker, more claustrophobic spaces with pipes, electrical conduits, and dripping water. This could be the procedural generator moving to an even more specialized texture set, one designed for areas players would only glimpse briefly in a normal game, but now it's creating entire levels from these maintenance area assets. The lighting in level 2 is described as more sporadic, areas of shadow broken by occasional work lights or emergency lighting. This makes sense from a technical perspective. The further you get from the intended play area, the less reliable the lighting systems become. Light probes might be placed incorrectly or not at all. Light maps might fail to generate. The engine falls back to even more expensive real-time lighting, but doesn't have proper sources placed, creating pools of darkness where no illumination reaches. The water or liquid presence in Level 2 is interesting. Most game engines have specific systems for water, special shaders, physics simulations, sound effects. If the procedural generator is trying to create wet or flooded areas, but doesn't properly initialize the water systems, you might get visual appearances of water without the proper physics. Or worse, you might get water physics without the visual, creating areas where movement is sluggish and sounds are muffled but nothing looks wet. The sensory disconnect adds to the wrongness of the space. Level 3 and beyond are where floating point precision decay starts becoming significant. At these depths, you're far enough from the noclip entry point that coordinates are getting large. The geometry becomes less stable. Walls might not be perfectly straight. Corners might not be exactly 90 degrees. These aren't stylistic choices, they're mathematical degradation. The procedural generation is trying to create precise architecture, but the coordinate system can't represent the precision needed. Entity behavior at these levels becomes more erratic, which tracks with AI pathfinding systems struggling with imprecise positions. An AI trying to navigate toward the player can't calculate exact paths when positions are rounding to coarse values. It might get stuck on geometry that appears smooth but has invisible precision-related bumps. It might path in circles because the navigation mesh, generated from imprecise coordinates, has subtle errors that create local minima in the pathfinding algorithm. Some levels are described as having impossible geometry, rooms that shouldn't fit within the space they occupy, corridors that loop back on themselves in ways that violate Euclidean space. As we discussed in the non-Euclidean section, this could be portal rendering, each doorway secretly teleporting you to disconnected spaces. But it could also be procedural generation errors creating geometry that intersects itself or extends in impossible directions because the collision checking between generated elements is failing at extreme coordinates. There are levels described as having shifting or changing layouts, where the environment literally reconfigures itself. This is cache coherency failure taken to an extreme. Not only is the system failing to remember what it generated, it's actively regenerating on a short time scale. Perhaps memory pressure is so high that chunks are unloading and reloading constantly. Perhaps there's a memory leak causing the system to run out of RAM and desperately thrash between different states. The environment changes not because it wants to, but because the system maintaining it is collapsing under its own instability. Certain levels are described as vast open spaces or endless voids. These could be regions where the procedural generation has failed entirely, producing no geometry at all. The renderer shows the skybox or background color, the physics simulation has no collision surfaces, and you're essentially in the void state we discussed earlier. Except instead of being a transitional state, before falling into another level, this is a destination. The generation algorithm looked at the coordinates, the seed values, the parameters, and produced nothing, an empty result. And the engine just accepted that and rendered the void. The extreme levels, those described with numbers in the hundreds or thousands, with reality-breaking properties and metaphysical impossibilities, would be at coordinates so extreme that multiple types of failures are compounding. Floating point precision is utterly degraded, measured in kilometers or worse. Procedural generation is producing output that barely resembles coherent geometry. portal rendering is creating connection graphs that are completely disconnected from spatial logic. Entity systems are spawning corrupted data that the renderer interprets as bizarre visual forms. At these extreme depths, the simulation is holding together by the thinnest thread. It hasn't crashed, error handling is preventing complete failure, but every system is operating at the edge of its tolerances. The output is technically valid program execution, but it's valid execution of algorithms that are being fed input so far outside their design parameters that the output is unrecognizable as the type of content they were meant to produce. This hierarchical breakdown, from the relatively stable level 0 through progressively more unstable levels to the reality-shattering extremes, makes perfect technical sense. It's what you would expect from a simulation that's running but degrading, where distance from the origin correlates with increased instability, and where each layer of system failure enables new types of impossibility. The Backrooms levels aren't arbitrary horror scenarios. They're a cataloguing of failure modes, each one representing specific technical systems, breaking down in specific ways. One of the most unsettling aspects of Backrooms lore is the sense that the environment changes when you're not looking, that rooms aren't quite the same when you return to them, that entities appear in places they couldn't have reached. This isn't just artistic horror. It can be explained through technical systems related to how game engines manage memory and state. Cache coherency in game development refers to the challenge of keeping multiple representations of the same data synchronized. A game engine might have geometry data in RAM, collision data in a physics system's memory, a rendering representation in GPU memory, and occlusion data in a spatial partitioning tree. When something changes, all of these representations need to be updated to match. If they don't update correctly, you get cache coherency failures. Different systems have different understandings of what exists and where. In a normal game, cache coherency is carefully managed. When an object moves, the engine updates its position in all relevant systems in a coordinated way. But in the backroom scenario, you're in space that wasn't designed to be cached and tracked properly. The systems that should be maintaining coherency don't know you're there or don't have proper data structures set up for the regions you're exploring. Here's what could happen. You walk down a corridor, the geometry generates and renders, the rendering system caches the visual data, the collision system caches the physics data, the procedural generation system marks that chunk as generated. But these caches aren't synchronized because you're in out-of-bounds space where the normal coordination doesn't occur. You walk away, the visual cache expires and dumps the data to save memory. You return, the rendering system regenerates the visual from the procedural algorithm. But the procedural algorithm runs with slightly different parameters, or the seed has drifted, or floating point errors have accumulated, and the new generation is different from the original. But here's the critical part. The collision cache hasn't expired. The physics system still has the old collision data. So now the visual geometry doesn't match the collision geometry. You see a wall in one position, but the collision boundary is actually a meter to the left. You see a doorway, but there's invisible collision blocking it. The space is inconsistent with itself because different subsystems are working from different cached versions of the data. This explains the backroom's experience of returning to an area and finding it changed. The visual changed because it regenerated. But other aspects, the sound occlusion, the AI navigation mesh, the collision boundaries, those might be from the old version or might have updated at different times, creating a Frankenstein combination of multiple temporal states of the same space. Memory leaks are another critical issue. A memory leak occurs when a program allocates memory but fails to release it when it's no longer needed. Over time, the program consumes more and more memory until eventually it runs out, causing performance degradation or crashes. But before it crashes, during the degradation phase, strange things happen. In the Backrooms context, imagine the procedural generation system is creating geometry as you explore, but the cleanup system that's supposed to delete faraway geometry isn't working correctly. Every corridor you visit allocates memory for its mesh data, collision data, light sources, texture allocations. You walk away and that memory should be freed, but it's not. The references aren't getting cleared properly, the garbage collection isn't running, the memory just accumulates. At first you don't notice. The engine has plenty of memory available, but as you explore for hours, visiting thousands of corridor segments and rooms, the memory fills up. The engine starts slowing down. It needs to be more aggressive about what it keeps in memory, so it starts dumping caches more frequently. This is when the visual inconsistency kicks in. Areas you visited recently are already being unloaded and regenerated because memory is tight. But worse, the memory leak isn't just holding on to geometry data. It might be holding on to entity instances. Every time the spawn system creates an entity, it allocates memory for that entity's state. Position, health, AI state, animation data. If entities aren't properly despawning when you move away from them, that memory accumulates too. You might not see them because they're outside your view radius, but they still exist in memory, still running their AI, still pathfinding, still trying to reach you. This creates the phenomenon of entities appearing in impossible locations. They're not teleporting supernaturally. They're existing in memory from when they spawned hours ago in a completely different part of the level. They've been pathfinding toward your position this entire time, following the AI navigation mesh through thousands of corridors, and now they've caught up, appearing in front of you in a location that seems impossible because you can't imagine how they could have navigated there. But they did, over dozens of hours of accumulated pathfinding through the leaked memory space. The memory leak also affects procedural generation in more subtle ways. The generation algorithm might rely on object pooling, reusing allocated memory for new objects rather than allocating fresh memory each time. But if the pool is corrupted by the leak, if old data isn't getting properly cleared, the new objects might have residual properties from old objects. A newly generated room might have entity spawn points from a completely different room type. Because the spawn point array wasn't zeroed out before reuse, this could explain why entity behavior is so inconsistent and unpredictable. They're spawning with corrupted initial states, mixing data from multiple different entity types, or from previous instances. The rendering shows one creature type, but the AI is running logic from a different type, because the AI state data got mixed up in the memory reuse. The result is behavior that doesn't match any designed pattern, because it's a hybrid of multiple patterns merged through memory corruption. There's also the issue of dangling pointers and use-after-free errors. These occur when code tries to access memory that's been deallocated. In a normal program, this causes a crash, but with error handling and safety checks, it might instead read whatever random data happens to be at that memory address now. In the Backrooms, this could manifest as entities or geometry, having properties that make no sense. A wall that has an entity's health value as its texture coordinate, producing a glitchy visual. An entity whose position is partially corrupted, causing it to jitter between valid positions and random positions, as different parts of the code read different corrupted values. The accumulating memory pressure and corruption also explain why deeper exploration leads to increased instability. It's not just distance from origin, it's accumulated memory corruption over time. The longer you're in the backrooms, the more memory leaks have accumulated, the more dangling pointers exist, the more cache coherency failures have compounded. The environment degrades not just spatially, but temporally. Some backrooms lore describes entities that seem to multiply or duplicate. From a technical perspective, this could be a cloning error in the object pooling system. When the spawn system needs to create an entity, it's supposed to get a clean object from the pool, initialize it, and place it. But if the pool management is corrupted, it might hand out the same pooled object to multiple spawn requests. Now there are multiple entities all sharing the same underlying data. When one moves, they all move. When one detects the player, they all react. The duplication isn't intentional, it's memory management failure creating multiple references to single instances. Or the duplication could be even more insidious. Every time the chunk containing an entity unloads and reloads, the spawn system creates a new instance because it doesn't remember the old one exists. But the old instance is still in memory due to the memory leak, just not being rendered because it's in an unloaded chunk. The entity effectively splits into multiple copies existing simultaneously in the same space, but only one rendering at a time depending on which chunk representation is currently loaded. This is the deep technical horror of cache and memory failures in the backrooms. The space isn't just geometrically unstable, it's temporally unstable. The present doesn't match the past because the systems maintaining continuity are failing. Memory that should be freed persists, creating ghosts of past states. Caches that should synchronize drift apart, creating inconsistent parallel realities within the same simulation. And all of this compounds over time, making escape not just spatially impossible, but temporally impossible. Because you can never return to a previous stable state when every moment adds new corruption to the accumulating chaos. The entities of the backrooms, the creatures and beings that populate the levels, are often described as moving in unsettling ways, unnatural gaits, appearing and disappearing, seeming to track you through walls, exhibiting behavior that's almost intelligent but fundamentally wrong. All of this can be explained through AI and pathfinding systems operating under corrupted or failed conditions. Start with navmesh generation. A navmesh is a navigation mesh, a simplified representation of the walkable areas in a level that AI characters use for pathfinding. The navmesh is typically generated automatically from the level geometry, marking areas where characters can stand and walk, and defining the connections between different areas. AI pathfinding algorithms like A** use this navmesh to calculate routes from their current position to target positions. In a properly designed level, the navmesh accurately represents the playable space, but in the procedurally generated, constantly shifting backrooms, navmesh generation would be a disaster. The system would try to generate navmesh data for each new chunk of procedural geometry, but the generation might not complete correctly. Connections between adjacent chunks might not be properly established. Vertical relationships might be wrong, marking areas as connected that require jumping or falling between them. The navmesh becomes a corrupted representation of space. An entity trying to pathfind toward the player using this corrupted navmesh would behave strangely. It might path to the edge of a navmesh island, stop, and then teleport to another island, because the pathfinding algorithm decided that's the next step in the route, not understanding that the islands aren't actually connected in real space. This looks like the entity disappearing and reappearing, but it's just following what its pathfinding data tells it is a valid route. Or the entity might get stuck in a loop, pathing back and forth between 2 points because the navmesh has a circular connection that the pathfinding algorithm can't resolve. From the player's perspective, the entity is pacing in a pattern, exhibiting what looks like patrol behavior, but it's actually just caught in a pathfinding loop due to corrupted data. The appearance of entities moving through walls can also be explained by navmesh errors. If the navmesh generation marked areas behind walls as walkable and connected, the AI will path through those areas. The entity's position updates to move through the wall, but the collision system might still be working correctly, creating a conflict. Different engines resolve this differently. Some teleport the entity to the nearest valid position. Others let the entity continue through the collision. Either way, the player sees an entity that doesn't respect walls, creating the impression of supernatural ability when it's actually just navigation data that doesn't match collision data. Entities described as stalking or following the player can be explained by AI systems that are partially working. The detection logic might be functioning, allowing entities to sense the player's position. The basic pathfinding might work for calculating a route. But the movement execution is corrupted. The entity pathfinds toward the player, gets close, but the behavior tree or finite state machine that should trigger attack or interaction behaviors doesn't transition correctly. The entity just continues pathfinding, staying near the player, following, but never executing the final interaction. This creates an entity that tracks you, that's clearly aware of you, but doesn't attack or interact in expected ways. It's stuck in a pursuing state because a state machine can't advance to the next state. The code that should trigger when it gets within attack range is either not running or not triggering the correct response. The entity is frozen in an intermediate behavioral state, caught between detection and action. The uncanny movement patterns, entities that move in jerky, non-fluid ways or that seem to glide, can be explained by animation and movement systems desynchronizing. The pathfinding calculates a smooth path and updates the entity's position along that path. But the animation system, which should be playing walk or run animations synchronized to the movement speed, is running at a different rate, or not at all. You get an entity whose position updates smoothly, but whose visual representation is either stationary, making it look like it's gliding, or updating at wrong intervals, making it look jerky. This is particularly unsettling because human brains are extremely good at recognizing natural movement. We can instantly detect when movement patterns are wrong. An entity that's gliding because its animations aren't playing hits our pattern recognition as fundamentally unnatural, even if we can't consciously articulate what's wrong. It triggers uncanny valley responses, the discomfort we feel when something is almost human or almost natural but subtly wrong. Entities spawning in impossible locations, appearing right in front of you or behind you without any visible approach, can be explained by spawn systems using incorrect position calculations. The spawn system tries to place an entity at a position relative to the player, perhaps 20 meters ahead in the direction you're facing. But due to floating point errors or coordinate system issues, the calculation produces a position that's actually right in front of you or even behind you. The entity spawns, and from the player's perspective, it just materialized out of nowhere. Or the spawn could be working correctly, placing the entity far away, but the rendering and culling systems are failing. The entity exists and is approaching, but it's not being rendered because it's incorrectly marked as not visible. Then suddenly the culling system corrects, realizes the entity should be visible, and it pops into view already very close. The entity didn't teleport, it was always there, but you couldn't see it due to rendering failures. Sound occlusion failures contribute to the uncanny feel. Entities should sound muffled when behind walls, louder when in open space, with acoustic properties matching the environment. But if sound occlusion isn't calculated correctly, you hear entities at full volume regardless of obstructions. They sound like they're right next to you when they're actually far away or behind multiple walls. This auditory disconnect from visual reality creates paranoia and spatial confusion. You can't trust your senses to accurately locate threats. The law often describes entities with specific behaviors. Some are attracted to noise, others to light, others seem to hunt in patterns. From a technical standpoint, these could be different AI behavior types using different stimulus response systems. An entity might have a sensor for audio sources and path toward loud sounds. Another might have a light level sensor and path toward illuminated areas. But if these sensory systems are receiving corrupted data, the behaviors become unpredictable. An entity that should be attracted to sound might instead be repelled because its audio sensor values are inverted. An entity that should hunt in a patrol pattern might chase the player aggressively because its patrol waypoints are all invalid and it defaults to player pursuit. Group behaviors and entity interactions could be even more corrupted. Flocking algorithms, where multiple entities move as a coordinated group, require entities to sense each other's positions and velocities. If that sensing is imprecise due to floating point errors, or if the flocking parameters are corrupted, you get groups that move in synchronized but unnatural ways, all turning at exactly the same instant, maintaining precise spacing that natural creatures wouldn't, moving in formations that look deliberate but are actually the output of corrupted math. Some entity behaviors might be the result of debug or test code that's still active. In normal game development, developers create test behaviors for prototyping, NPCs that always path to the player, that spawn in infinite numbers for stress testing, that exhibit simplified behaviors for verifying systems. This code should be removed or disabled in the final game, but what if the Backrooms has this test code still running? You encounter entities exhibiting pure test behaviors, mechanically simple responses that were never meant to be seen by players, creating the impression of entities that are simultaneously menacing and oddly simplistic in their behavioral patterns. The most disturbing possibility is entities that actually corrupted player data or duplicated player instances. If the spawn system is completely broken and is trying to spawn entity types that don't exist in its tables, it might grab whatever data it finds in memory. If player character data happens to be in that memory region, you might encounter entities that look like the player character, that move using player movement code, that have player attributes. Encountering yourself, or a version of yourself that's acting like a hostile entity, is the ultimate technical horror. The system is so corrupted it's cannibalizing its own data to create threats. All of these AI and pathfinding failures combine to create entities that are deeply unsettling, not because they're well-designed monsters, but because they're broken simulations exhibiting the uncanny wrongness of systems that are trying to function, but fundamentally can't. They're the visible manifestation of code operating outside its design parameters, producing outputs that are valid at the machine level but horrifying at the experiential level. Now we arrive at the philosophical and speculative layer. Everything we've discussed so far has been about technical failures in game engines, but there's a deeper question the Backrooms community sometimes explores. What if our reality is itself a simulation, and the Backrooms represent glitches in that base-level simulation? This is where technical analysis becomes metaphysical speculation, but it's worth exploring because it highlights why the technical interpretation of the Backrooms is so compelling. If reality is a simulation, it would need to operate on principles analogous to game engines, discrete time steps, finite precision for positions and values, optimization strategies to avoid calculating things that aren't observed, procedural systems to generate content efficiently. In this framing, noclipping out of reality isn't about entering a video game, it's about finding a glitch in the base simulation that allows you to access the computational substrate. The yellow hallways aren't generated by some external game engine. They're what the universe's own generation algorithms produce when they're forced to create space in regions that should be inaccessible. The entities aren't coded monsters. They're spurious patterns emerging from the simulation's attempt to populate space that shouldn't exist. This interpretation treats all the technical failures we've discussed not as metaphors, but as literal descriptions of reality's own machinery breaking down. Floating point precision decay isn't analogous to something in base reality. It is what happens when you get far from reality's origin point in its coordinate system. Non-Euclidean geometry isn't a rendering trick. It's what space actually does when the simulation's portal-based optimization systems are exposed. Entities aren't broken AI. They're the simulation's debugging systems or autonomous cleanup processes that become visible when you're in regions they're actively trying to repair or quarantine. The appeal of this interpretation is that it provides a unified explanation for both the backrooms as fiction and the technical systems as real. All the game engine failures we can document and study in actual games become evidence for how reality itself might fail. The backrooms becomes a thought experiment. If our universe is computational, these are the glitches we should expect to find. There are real physicists and philosophers who take simulation theory seriously, who argue that we might genuinely be in a computational substrate of some kind. They point to things like the quantization of energy and space at the Planck scale, the finite speed of light creating a horizon beyond which causality doesn't propagate, the apparent fine-tuning of physical constants, and the weird non-local correlations in quantum mechanics as all being consistent with living in an optimized simulation. In this framework, the Planck length is the floating point precision limit of reality, the smallest representable distance. The light speed limit is the maximum propagation rate for state updates in the simulation. The cosmological horizon is occlusion culling at universal scale. Reality doesn't calculate what's beyond your causal reach. Quantum superposition is reality not calculating a definite state until observation forces the calculation to run. These are all optimizations a simulation would use, and if reality is optimized like a game engine, it has the same vulnerabilities. There should be edge cases where the optimization breaks down, regions where precision degrades, boundaries where the generation algorithms produce corrupted output, places where the collision detection fails and you can slip through to somewhere you shouldn't be. The backrooms in this view isn't fiction inspired by games. It's a documentation of what actual reality glitches would look like, informed by our understanding of computational systems. But we have to be careful here. This is speculation, not science. We have no evidence that reality is a simulation, and the backrooms is fiction created by people who understand game engines, not a genuine report of reality glitches. The technical resonance exists because the creators understood the systems they were describing, not because those systems actually govern reality. What we can say is this: the backrooms works as horror because it leverages our intuitive understanding of how computational systems fail. We've all experienced game glitches, seen the behind-the-scenes machinery when it breaks through into visibility. The backrooms takes those experiences and extrapolates them into an environment asking, what if you got trapped inside the glitch? What if the broken system kept running, kept trying to simulate, but everything was wrong? The power of this premise is that it's both completely fictional and deeply rooted in reality. It's not real, but it could be given the right technical setup. It's not possible in our universe, but it's possible in any sufficiently complex simulation. And because we interact with such simulations constantly, Through games and virtual environments, we have first-hand experience of what they're describing. This creates a unique form of technical horror that's grounded in verifiable, understandable system behavior. You're not afraid because something is unknowable and alien. You're afraid because you understand exactly what's happening. You can trace the cause and effect chain from collision failure to procedural generation to floating point decay, and that understanding shows you there's no escape. The system will keep failing in consistent ways. You can predict the failures, but you can't prevent them. In a supernatural horror story, there's always the hope that the rules might change, that the monster might not appear, that some intervention might save you. But in technical horror, the rules are deterministic. The code executes the same way every time. The failures follow predictable patterns. You can understand the system completely and still be powerless against it, because you're inside it, and it's the foundation of your existence. The Backrooms as reality simulation glitch is the ultimate expression of this. You haven't escaped reality. You've fallen through it into the computational layer beneath, and that layer operates on logic that your mind can grasp, algorithms you can understand, failures you can predict. But understanding doesn't grant control. The simulation runs, the algorithms execute, the failures compound, and you're just data being processed by systems that don't care about your continued existence, only about their own mechanical operation. This is why the technical interpretation matters, even though the Backrooms is fiction. It teaches us something about the relationship between understanding and power. You can comprehend every detail of how a system works and still be subject to it. Knowledge doesn't inherently grant escape. Sometimes it just makes you more aware of why escape is impossible. Let's ground this back in documented reality by examining actual game glitches that exhibit Backrooms-like properties. These aren't speculation. They're observed phenomena that players have encountered and documented, and they demonstrate that everything we've described is based on real system behaviors. The Minecraft Farlands, which we've mentioned before, are perhaps the most famous example. In Minecraft versions before Beta 1.8, travelling beyond approximately 12,783,000 blocks from spawn would cause terrain generation to break down spectacularly. The noise functions that generate smooth, natural-looking terrain would start producing extreme values due to floating point precision loss. This resulted in massive walls of terrain shooting up to build height, impossible overhangs, and bizarre patterns of blocks that couldn't exist in normal terrain generation. Players who made the long journey to the Farlands documented the experience. The increasing instability as they approached, blocks starting to flicker and act strangely, entities beginning to behave erratically, performance degrading as the game struggled to process the corrupted terrain data. This is real-world evidence of exactly the kind of coordinate distance-based degradation we've described for deep Backrooms levels. Interestingly, Minecraft later fixed this by implementing better handling of large coordinates, but the Farlands remain as a snapshot of what happens when procedural generation systems encounter the limits of floating point precision. The community's documentation of the Farlands, including the psychology of travelling through increasingly glitchy space to reach them, directly parallels Backrooms exploration narratives. Skyrim's out-of-bounds spaces provide another instructive example. Through various collision glitches like plate launching or exploiting horse physics, players can get outside the intended playable area. What they find is technical infrastructure, low-resolution meshes used for distant views, trigger volumes floating in space, testing areas the developers used for prototyping. These spaces exist but were never meant to be accessed. They have the eerie quality of being simultaneously part of the game world and completely outside normal gameplay, much like the backrooms existing in game space but outside playable reality. Half-Life 2 and other Source Engine games have extensively documented out-of-bounds regions. Speedrunners and explorers have mapped the void spaces behind and beneath maps, finding optimization geometry, area portal markers, and the various technical elements that make the engine function efficiently. They've also documented what happens when you noclip far from the map origin. Rendering starts to break down, physics becomes unstable, entities behave strangely. The source engine's internal limitations become visible as you push into extreme coordinate spaces. One particularly relevant source engine phenomenon is the accelerated backhopping movement glitch. By exploiting how the engine calculates friction and acceleration, players can build up enormous speeds while moving backward. At extreme velocities, collision detection can fail entirely, allowing passage through walls. This isn't just similar to noclipping, it demonstrates the specific failure mode. Velocity exceeding what the collision system was designed to handle, resulting in boundary penetration. Grand Theft Auto games have multiple relevant glitches. The blue hell glitch in various GTA titles refers to falling through the ground into a blue void beneath the game world. The world continues to render above you. NPCs continue their routines, the simulation keeps running, but you're in a space you were never meant to access. Some areas of blue hell have partial geometry, roads without buildings, buildings without interiors, showing the optimization and level of detail systems at work. GTA also has documented issues with entity spawning and despawning. Drive too fast through the city and the spawn system can't keep up, leading to empty streets that suddenly populate when you stop. Or you'll see entities spawning into walls or appearing in mid-air because the spawn position calculation referenced geometry that wasn't loaded yet. These are real examples of the kind of entity behavior inconsistencies we'd expect in the backrooms. No Man's Sky provides an example of procedural generation at massive scale. With 18 quintillion planets, the game uses seed-based generation extensively. But players have documented cases where planetary generation produces bizarre results. Floating structures, terrain that intersects itself, buildings spawning inside mountains. These are edge cases where the generation algorithms produce technically valid but practically nonsensical output. The game has also had issues where planets change appearance between visits if generation parameters are updated, creating an experience similar to the backroom's unstable geography. Pokémon games have glitches like Hall of Fame corruption, where corrupted data from one system bleeds into another, causing text from one part of the game to appear in another, or sprites to display with wrong graphics. This is real-world evidence of memory corruption creating visual and behavioral anomalies, exactly the kind of thing that would make backrooms entities appear wrong or hybrid. Dark Souls has the chain backstab glitch where precise positioning and timing can lock an enemy into an infinite backstab loop. The AI can't escape because its state machine has entered a configuration that the designers didn't anticipate. This demonstrates how AI systems can get stuck in behavioral loops when conditions outside their design parameters occur, explaining Backrooms entity behavior loops. Super Mario 64 has parallel universes, a glitch discovered by speedrunners where extremely high speeds combined with the game's position handling can cause Mario to exist in copies of the level at coordinates offset by multiples of 65,536. These parallel copies have collision but no graphics, allowing movement through walls in the visual level by actually being in a different coordinate space. This is a real implementation of non-Euclidean space. position and visual representation not matching due to coordinate overflow. Gary's mod, with its physics sandbox, regularly produces glitches where stacked objects suddenly explode or phase through walls as the physics solver fails to resolve complex interactions. Players have created scenarios that deliberately break the physics engine, creating entities that vibrate violently, clip through geometry, or launch at absurd velocities. These demonstrate real physics system failures, creating impossible movement and positioning. Portal itself, despite being a game about portals, has glitches. Speedrunners can achieve velocities high enough that they pass through portals without transitioning, or transition multiple times in a single frame, creating positional and velocity states the game wasn't designed to handle. The carefully controlled non-Euclidean space of Portal can break down into genuinely glitched space when pushed beyond design limits. All of these examples from real games demonstrate that the technical failures described in the Backrooms aren't hypothetical. They're documented, reproducible phenomena that players have found by pushing games beyond their design parameters. The Backrooms synthesizes these real glitches into a coherent environment, asking, what if you couldn't escape? What if the glitch was the entire world? The genius of the Backrooms as a concept is recognizing that these glitches share common properties. They create spaces that feel wrong, that don't follow expected rules, that exist as technical artifacts rather than designed content. By understanding what these spaces have in common and extrapolating that into an endless environment, the Backrooms becomes a catalogue of every type of game glitch folded into one nightmare space. And because these glitches are real and documentable, the Backrooms carries a weight that purely imaginary horror doesn't. Someone reading about the Backrooms who has experienced the Far Lands, or fallen through the map in Skyrim, or noclipped in Half-Life, recognizes the technical authenticity. They know this could happen. They've seen the pieces of it in different games. The Backrooms just combines all those pieces into a single coherent vision of what living inside broken simulation would be like. We've travelled deep into the technical infrastructure of the Backrooms, examining collision detection failures, procedural generation corruption, non-Euclidean rendering, floating point precision decay, cache coherency issues, AI pathfinding errors, and the philosophical implications of simulation theory. What emerges is a picture of horror that's uniquely modern, uniquely tied to our computational age. The Backrooms frightens us not through the unknown, but through the known breaking down. It's not about monsters we can't understand. It's about systems we understand perfectly continuing to operate while producing outputs that violate our expectations of reality. It's horror through technical correctness, producing existential wrongness. There's a profound discomfort in watching a system do exactly what it's designed to do while creating an environment that shouldn't exist. The procedural generation algorithm is working correctly, executing its code without errors, and the result is an endless maze. The collision detection is functioning as programmed, checking boundaries and resolving penetrations, and the result is walls you can fall through. The AI pathfinding is following proper A-star algorithms with valid heuristics, and the result is entities that move in uncanny patterns. This is different from traditional horror where the threat comes from outside normal reality. In the Backrooms, you're still inside reality, but you've found a part of reality where the normal rules produce abnormal results. It's not that physics has stopped working, it's that you're at coordinates where physics produces instability. It's not that the simulation has failed, it's that you're in a region where the simulation generates content it was never meant to generate. The technical analysis we've conducted reveals the Backrooms as perhaps the most elaborate technical thought experiment in modern horror. it asks. If reality is computational, what do its failure modes look like? And it answers with remarkable consistency. They look like every documented game glitch, extrapolated to infinite scale and combined into one nightmare environment. But there's also something beautiful in this technical horror. It's a celebration of how much we've learned about computational systems, how deeply we understand the machinery that creates our virtual worlds. The Backrooms could only exist as a concept in a culture that has spent decades exploring, documenting, and understanding game engines. It requires a shared literacy of glitches, an intuitive grasp of how simulations work and fail. Every person who's experienced a game bug contributes to the collective understanding that makes the Backrooms resonate. The speedrunner who has exploited collision detection for faster times, the player who has explored out-of-bounds spaces just to see what's there, the developer who has debugged procedural generation algorithms and seen the bizarre outputs they produce under edge conditions, the graphics programmer who understands why precision degrades at extreme coordinates. All of these experiences feed into recognizing the technical authenticity of the Backrooms. This creates a form of collaborative horror, where the community collectively understands the systems being described, collectively recognizes the accuracy of the technical details, and collectively contributes to elaborating how these systems would interact. The Backrooms wiki isn't just creative fiction, it's technical documentation of impossible spaces, with different contributors adding insights about different failure modes and edge cases. The levels aren't arbitrary, they're a progression through different types of system failure. The entities aren't random monsters, they're specific examples of AI corruption and spawning errors. The geometry isn't just weird for the sake of being weird, it's implementing actual techniques for creating impossible spaces. The whole thing is rigorous in a way that horror usually isn't, constrained by technical possibility rather than freed by supernatural arbitrariness. This rigor is what makes it compelling to a technically literate audience. You can analyze the Backrooms, trace the cause and effect chains, predict what should happen in unexplored regions based on the established technical rules. It's world building through system design rather than through narrative invention. And paradoxically, that makes it feel more real, because systems are consistent in ways that stories often aren't. The Backrooms also serves as a mirror to our relationship with technology and simulation. We spend enormous amounts of time in virtual spaces, games, virtual reality, social media environments, digital workspaces. We understand intuitively that these spaces are constructed, that they run on code, that they can glitch. The Backrooms takes that understanding and asks, what if you got trapped? What if the glitch became your reality? It's a very modern fear. The fear of being trapped inside malfunctioning technology, unable to escape to the real world. It resonates because we've all felt a version of it. The frustration of software that won't close, the disorientation of a game that's glitched into an unplayable state, the unsettling feeling when technology behaves in ways we don't expect or understand. But the Backrooms takes this mundane frustration and elevates it to existential horror. You're not just stuck in a buggy program you can quit, you're stuck in a broken reality with no exit. The technology isn't just malfunctioning, it's the substrate of your existence. And it's going to keep failing, keep degrading, keep producing increasingly unstable outputs, because that's what systems do when they're operating outside their design parameters. There's also something profound in the idea that understanding doesn't equal control. We can trace every technical detail of how the Backrooms would work, explain every glitch, predict every failure mode, but that understanding doesn't provide escape. The systems will execute as systems do, following deterministic rules to produce outputs that trap you more surely than any supernatural curse. This is the horror of being subject to mathematics, to algorithms, to the mechanical operation of code. You can understand it completely and still be powerless. The collision detection will fail in predictable ways. The procedural generation will create infinite spaces according to knowable rules. The floating point precision will decay at calculable rates, all predictable, all understandable, all inescapable. In the end, the backrooms represent something unique in the landscape of horror. A technically rigorous exploration of what broken simulation would be like from the inside. It's collaborative technical documentation, masquerading as creative fiction. Or perhaps it's creative fiction that achieves its effects through technical accuracy. Either way, it stands as a monument to our collective understanding of computational systems and how they fail. The yellow hallways aren't just scary because they're endless. They're scary because we understand exactly how the procedural generation would create them, and that understanding tells us there's no exit. The entities aren't just threatening because they're hostile. They're threatening because we can see their corrupted AI following broken pathfinding, which means their behavior will be unpredictable, but not random, patterned, but not logical, simulatable, but not escapable. This is the beauty of broken systems. They continue to operate, continue to follow their programming, continue to produce outputs, even when those outputs are nightmares. The backrooms is what happens when you're inside such a system, when you are data being processed by algorithms that don't know you're there and wouldn't care if they did. It's the computational sublime, the terror and wonder of being subject to systems too large and too precise to escape. As you drift off to sleep listening to this analysis, perhaps you'll dream of yellow hallways, of flickering fluorescence, of entities moving in uncanny patterns through impossible spaces. And maybe, just maybe, you'll understand them not as supernatural horrors, but as what they truly are. The faithful execution of deterministic algorithms operating on corrupted input, producing outputs that are mathematically valid but experientially impossible. You'll understand that the real horror isn't the monsters or the maze. It's being trapped inside a system that is working exactly as designed, following every rule correctly and creating hell through proper operation rather than through malfunction. The code runs clean. The algorithms execute without error. The systems function correctly, and the result is the backrooms. Sleep well in your reality and hope that the collision detection never fails, that the coordinates stay precise, that the procedural generation never receives your position as input. Hope that you never noclip, never fall through the floor of reality into the computational substrate beneath, because if you do, now you understand exactly what you'll find there. The machinery, always the machinery, executing faithfully, creating endlessly, trapping completely. Welcome to the technical specification of liminal horror. Welcome to the backrooms.